If you've spent any serious amount of time with large language models, you know that initial feeling, whether it's for work or just, curiosity.
Oh yeah, that initial magic is it's intoxicating.
Absolutely. The speed, the fluency, the just sheer breadth of knowledge it seems to have.
It feels like you have this lightning-fast library right at your fingertips.
Yeah.
It can synthesize information in ways we didn't think were possible just a few years back.
But then there's that persistent, frustrating, and frankly, dangerous underbelly to all that magic.
The confident hallucinations.
Exactly. The confident hallucinations, the failures that come out of nowhere, and that truly catastrophic collapse the second the data shifts even a little bit outside its training set.
And those out-of-distribution failures, or ode failures, they're notorious.
And we've all heard the advice, right? Just keep scaling, throw more data at it, more parameters, more compute. Just follow those empirical scaling laws and hope that brute force fixes the structural issues.
And yet, here we are. We've gone from billions of parameters to, rumored trillions. We're training on these astronomical data sets. But those core problems, that foundational incoherence, that unpredictability, they persist.
The models get bigger, but do they really get smarter in a way that's robust or reliable or even just honest?
That's the question. They don't seem to be getting structurally sounder.
Exactly. And that brings us right to the mission of this deep dive. Today, we're immersing ourselves in a piece of theoretical work that makes a pretty radical argument.
The argument being that these failures are not about a lack of data or compute.
Not primarily, no. The paper argues it's a fundamental mistake in geometry. We are diving into the Lorentz-Manifold Transformer paper, or LMT.
And this is a proposed theoretical framework designed to tackle that deep intrinsic structural robustness by changing the very shape, what they call the geometric substrate where knowledge lives.
It's such a different way of looking at the problem. If you think of an AI's knowledge as this incredibly complex, high-dimensional map.
The paper basically suggests we've been trying to map the whole world, which is spherical and exponentially branching, using a flat piece of graph paper.
And that mismatch, that's what they say is the root of the instability we're seeing.
It's a structural argument from the ground up.
Okay, now before we even start pulling apart the math and the mechanisms here, we have to put a huge warning sign right at the top.
A very, very crucial piece of context.
The LMT is emphatically not a production model. You can't go download this and run it today.
Right. It is explicitly defined as a theoretical framework and a research platform. That's it.
Its design deliberately prioritizes mathematical clarity, these topological guarantees, over just raw speed.
Absolutely. We're talking about a computational complexity of ON2.
Yeah.
For anyone who works with large models, that number basically screams intentionally inefficient.
And that's a feature here, not a bug. It's part of the research design.
Precisely. You should think of the LMT as this high-powered, custom-built lab instrument. It's a tool for researchers to test fundamental ideas about geometry and dynamic constraints.
So it's not trying to compete with, say, Mamba or flash attention on speed.
Not at all. Or even with other hyperbolic models like HipFormer that are built for efficiency. This paper is asking a much more foundational question. What is the mathematically correct structure needed to represent complex hierarchical knowledge?
And can we prove that that structure leads to more predictable, safer behavior?
That's the whole game right there.
Okay, so let's unpack that core idea. Why is the shape, the geometry of this data space so critical? Why can't the standard transformer, which is obviously proven it can learn language, handle this?
We should start with that analogy the authors use, because it's really the perfect entry point, the flat map distortion.
Right. Imagine trying to map the Earth.
Exactly. The Earth's surface, especially when you think about all the complex relationships on it, like, say, transportation networks or ecosystems, it's this continuous, three-dimensional, highly branched thing.
And when cartographers try to represent that on a flat, two-dimensional piece of paper like a Mercator projection, you get distortion. It's a geometric necessity.
It's inevitable. The classic example everyone points to is Greenland versus Africa.
On a flat map, Greenland looks absolutely enormous. Sometimes it looks even bigger than Africa.
Even though Africa's actual landmass is 14 times larger, the distortion happens because you have to stretch and tear the geometry to force a sphere into a flat rectangle. Points that are far apart at the poles get forced into these unnatural, warped relationships.
Okay, so the parallel is immediate. The AI model is trying to map the concept space of human knowledge, which is hierarchical, branching, and exponential.
And it's forcing that complex spherical reality onto a flat Euclidean map.
That's the core of the problem right there.
That's the core mechanism of failure. Standard transformers operate in what we call flat Euclidean spaces, Rn, where distance is just the straight line we all learned about.
But data like human language or a biological taxonomy,
Phylum, class, order, family.
or even just how meaning is built compositionally, all of that is intrinsically tree structure.
And those structures grow incredibly fast.
Exponentially fast. For a tree structure with a certain depth, D, and a branching factor, B, you get something like OBD nodes.
Yeah, just think about trying to catalog every species on Earth or every possible grammatically correct sentence in English. The conceptual space just explodes as you go deeper.
So you have this exponentially growing problem.
That you're trying to cram into a space designed for slow polynomial growth.
And what do the researchers call that specific mismatch?
They define it as the geometric capacity bottleneck. And it's so important to get this. This isn't about running out of RAM or having too few parameters.
Okay.
The model could have 1 trillion parameters, but if the geometric substrate is wrong, the model literally runs out of structurally meaningful room to place concepts without distorting their relationships.
It's an information theoretic limit, not a hardware limit.
Purely imposed by the shape of the manifold.
Let's dip our toes into the math just a little bit here. The paper talks about this volume growth dichotomy. What does that prove about our standard flat spaces?
It just details that core mathematical incompatibility. In a standard Euclidean space, Rn, the volume of a sphere grows polynomially with its radius, r. It's proportional to Rn.
So slow and steady growth.
Very slow, very predictable. You double the radius, the volume increases by a factor of 2 ln's. It's linear growth per dimension.
But our knowledge structure demands exponential growth just to keep things straight.
Precisely. The data capacity requirements just explode. And according to manifold capacity theory, this forces a trade-off. You have to pick between 2 really bad outcomes.
So what's the lesser of 2 evils for the model?
Well, the first choice is compression. To fit everything in, the model could just squish the semantic radii of every concept down to almost nothing.
So everything gets jammed together.
Everything gets blurred. The boundaries between dog, wolf, and fox might just disappear.
Yeah.
The model becomes imprecise.
Okay, that's one bad option. What's the other?
The other, and the more dangerous one, is distortion. To make room, the model is forced to map semantically distant nodes concepts that should be worlds apart into nearby neighborhoods. It just has to, because the geometry can't support the real distance.
So the model is physically forced to create these false shortcuts in its own mental map just to fit everything in?
That's a perfect way to put it. And they quantify this. The capacity ratio for hyperbolic space versus Euclidean space shows this monumental exponential advantage. It basically proves mathematically that Euclidean space is fundamentally incapable of hosting deep hierarchies without this distortion.
So it's not a matter of opinion. It's a geometric necessity to use curved space.
It's a necessity if you want to maintain proportional distances and structural fidelity.
Okay, let me play devil's advocate for a second. Couldn't a huge Euclidean model, I don't know, one with 10 trillion parameters, just learn some kind of really complex nonlinear mapping that approximates the right curvature internally, even if its base is flat?
That's basically the scaling hypothesis we've all been operating on, right? And this paper offers a geometric counterpoint. Massive scale can approximate local curvature. You can flatten a small piece of a sphere.
Sure, a small town looks flat.
But you can't flatten the whole globe without that massive distortion we talked about, usually far away from where you started. So even if the model learns a clever function, that function is still trapped by the polynomial volume growth of Rn. The distortion just gets shoved into another part of the map.
And usually into the parts that represent the deepest, most abstract relationships.
And that, right there, is where the confident hallucinations come from.
Let's trace that path. How do we get from a distorted geometric map to a confident, plausible-sounding lie?
Okay, so if the model has run out of space to properly separate, say, dog, a biological concept, from galaxy, a cosmological one.
Concepts from totally different, very deep hierarchies.
It's forced to place them in unnaturally close neighborhoods. It creates what the paper calls geometric wormholes.
I love that term. A geometric wormhole. A shortcut that looks real on the map, but violates the underlying structure of reality.
And when you ask the model a question that pushes it to the edge of its knowledge, maybe just a little outside its training data,
It defaults to these fake nearby connections.
the optimization algorithm sees this false shortcut as locally optimal. It satisfies the immediate task, it lowers the loss function, even though the resulting statement is globally, fundamentally incoherent.
And the confidence. Why is it so sure of itself?
Because in its internal distorted geometric map, those two concepts are right next to each other. It's not guessing, it's just reporting an adjacency that the faulty geometry forced upon it.
So it's a failure of geometric fidelity, not a memory slip or a lack of data. It fundamentally misunderstood the structure of reality because it was using the wrong kind of map.
That's the argument.
This makes the case for geometry seem airtight. If flat maps fail, we need curved maps, specifically maps that expand exponentially as you move outwards. So how does this LMT paper introduce the right kind of curvature to solve this?
The solution, as we've hinted, is in spaces of constant negative curvature. This is known as hyperbolic geometry. And this geometry is mathematically proven to have that crucial, rapid, exponential volume growth.
So it's the perfect geometric match. As the hierarchy gets deeper and your radius increases, the available space just explodes to accommodate all the new concepts without squishing them.
It allows you to embed these deep, complex trees with bounded distortion. That means the proportional relationships, the relative semantic distances, they all stay intact.
Now, the LMT specifically uses the Lorentz model of hyperbolic space. This seems important because I know a lot of previous work in this area used something called the Poincare ball model. Why the switch?
That's a really key engineering detail for deep learning. The Poincare ball is intuitive to visualize, but it struggles with numerical stability, especially for representations that get close to the edge of the ball.
Which is where the concepts deep in the hierarchy would live.
Exactly. And when you try to optimize near that boundary, you can get vanishing or exploding gradients. It's a nightmare for training a deep network.
So the Lorentz model is a safeguard for stability. It's defined in a higher dimensional space, which sounds more complicated, but I guess it makes the math cleaner for the computer.
It makes the math much cleaner for optimization. The Lorentz model avoids those boundary issues. And importantly, the way it defines distance enables more efficient computation during the attention part of the model.
How so?
It avoids using complex functions, like the inverse hyperbolic cosine in the forward pass. Those are computationally expensive and can introduce all sorts of numerical noise or instability, especially in a very deep network.
Wait, for those of us who aren't mathematicians, why is avoiding a function like that a big deal? Is it just about speed?
It's speed and stability, but stability is the really big one here. Hyperbolic geometry needs these functions to calculate distance on the curved surface. If those calculations have even tiny numerical errors, tiny rounding errors, they compound over hundreds of layers.
And eventually, they can corrupt the entire structure.
Right. So by choosing the Lorentz model, the authors found a way to express that distance that is mathematically equivalent, but numerically much simpler and safer for the optimization process.
Okay, that's fascinating. So we've solved the spatial problem. We've moved to this stable, negatively curved space. But you said earlier, geometry alone isn't enough for sequences. A static map doesn't tell you about the flow of language.
No, it doesn't.
No.
You need dynamics, you need temporal context, and you need to solve what's known as the temporal binding problem.
What's that exactly?
Previous work with hyperbolic geometry was great for static knowledge graphs, classifying species, but a transformer needs to understand which features in a sentence belong together right now. If I say, the quick brown fox jumps, the model has to bind quick, brown, and fox together as a single unit in that moment. That's the binding problem.
And the LMT solves this with something called HA core N.
Yes, the hyperbolic artificial Kuramoto oscillatory neurons. It's a bit of a mouthful.
It is.
But what it does is it generalizes the standard Kuramoto oscillator model, which is well known in neuroscience for modeling how things synchronize, and applies it to the negative curvature of this Lorentz manifold.
So let's use the analogy. How does adding this musical dimension solve the binding problem?
Think of it like an orchestra or a room full of metronomos. Every concept, every word, is its own little oscillator trying to find a rhythm.
Okay.
When these oscillators are coupled, when their features interact in the model, they start to synchronize their phase. If two concepts in the AI model synchronize their phases, it's a signal that they are temporally and semantically bound together in that moment.
Even if they're really far apart in the giant hyperbolic space.
Exactly. So even if mammal and dog are geometrically distant because the hierarchy is so deep, if they're used together in a sentence, their little metronomos start ticking in sync. It tells the model, hey, these two things are relevant to each other right now.
It adds a rhythmic temporal layer on top of the static map. It's not just where the concepts are, but when they're active together.
And in the LMT, the math guarantees that this synchronization corresponds to movement along parallel geodesics in the manifold.
Geodesics being the straightest possible lines in curved space. So by making them synchronize their rhythm, you're also forcing their trajectory to be consistent and predictable within the geometry.
And that's the crucial distinction. A standard recurrent neural network can update its state in any arbitrary way it learns. H-acorn forces a continuous geometric constraint. The state has to flow along these geometrically defined paths.
That sounds like a much stronger inductive bias for the model to work with.
It's a very strong bias for preserving consistency over time. The model can't just jump anywhere to minimize the immediate loss. It has to respect the underlying curve structure as it processes the sequence. It keeps the dynamics from breaking the map.
And what if two concepts are not supposed to be together? What if their rhythms are totally out of sync?
That's where the coherence gating mechanism comes in. The attention weights in the transformer are directly modulated by the phase coherence. If two features are out of sync, their metronomos are all over the place, the gate acts like a filter.
A topological noise filter, they call it.
Yes, and it suppresses the information flow between them.
That's really interesting. It's not just a probability-based filter, it's a structure-based one.
Oh.
The model can geometrically refuse to attend to something if it determines, based on phase, that it doesn't belong.
Even if the raw dot product attention score is high, structure, coherence, and geometry are guiding the attention, which should lead to much more robust and less spurious connections.
So from there, the paper moves from just making a more efficient model to making a safer one, which I think is maybe the most compelling part of this research.
It's a huge part of the argument, yeah. The mathematical rigor here isn't just for show. It directly leads to more robust and, counterintuitively, safer outcomes.
Okay, let's start with the current problem. What's wrong with today's models in a safety context?
The authors use this great term, the zombie model problem. It's meant to define how standard large models behave when they're pushed into these ambiguous or out-of-distribution scenarios.
A zombie model, and what defines that?
It's defined by monotonic linear degradation. So as the data gets weirder or the question gets harder, the model's performance gets steadily linearly worse.
Okay, that makes sense.
But, and this is the critical part, it maintains high confidence in its flawed answers. It becomes functionally incompetent while remaining completely convincing.
It's like an overconfident person who is totally lost but just keeps making things up with complete authority.
Exactly. And that's an opaque, unpredictable failure mode. It's disastrous in high-stakes situations. You can't have an AI for, say, medical diagnosis that silently degrades while telling you it's 99% certain.
You can't trust it. So the LMT is designed for a completely different kind of failure.
A preferable one, they argue. It's designed for MDAS stability, so it maintains high performance, gives you structurally consistent results, right up until it hits a critical threshold of data incoherence.
And at that point,
it's designed to collapse, abruptly. They call it a phase transition failure mode. The system is engineered to basically say, this information violates my structural rules, so I'm stopping.
why is a model that just breaks visibly safer than one that lies convincingly?
Predictability and interpretability. A sudden, visible failure gives you an immediate, unambiguous signal that something is wrong. It establishes a verifiable boundary of trust.
You know exactly when it has failed.
And knowing that the structural integrity is gone is infinitely better than relying on a plausible but deeply flawed answer.
Okay, so to make this failure predictable, you need a way to measure that it's about to fail. That's where they bring in this idea of geometric frustration.
Yes, geometric frustration, or F, is the core technical innovation for safety. It quantifies the conflict between two forces that are always acting on the model during learning.
What are those two forces?
On one hand, you have the model's immediate goal, the task loss, answering the question. On the other, you have its commitment to its foundational structure, the structural loss.
How do you measure a conflict like that?
You look at the gradients during optimization. The frustration metric, F, is highest when the task gradient, the direction the model wants to move to answer the question, is directly opposed to the geometric gradient, the direction it needs to move to keep its map of the world intact.
It's like the model is being told, to answer this question, you have to tear your own map.
That's a perfect analogy. When F is high, the model is under geometric stress.
Yeah.
It's being forced to violate its own structural rules to satisfy a short-term goal. And that misalignment is a direct precursor to hallucination.
So by monitoring F, you can see the failure coming before it happens.
You can anticipate the structural failure before it manifests as a coherent lie.
And to enforce that structural fidelity, they needed a way to measure structure itself, a way that's independent of how the model is storing things internally. This brings us to the Gromov-Wasserstein distance.
Right. The GW distance is a very powerful mathematical tool because it compares the relational structures of two different spaces without caring about their coordinate systems.
So it's coordinate-free.
It is. Imagine you're comparing two city maps. You don't care if one is rotated or scaled differently, you just care if the relationships are the same. If city A is 50 miles from B and B is 10 from C, is that preserved on both maps?
So the LMT is trying to minimize this GW structural risk. It's making sure its internal map of concepts has the same relational structure as the real data.
Globally, not just locally. It's a topological guarantee that the map represents the territory faithfully.
Okay, let's talk about the proof. They ran these synthetic experiments to really isolate these effects. Tell us about the color ring experiment.
This was just a beautiful, clean validation. They created a data set of points sampled from a perfect circle, an S1 topology, but they embedded it in this high-dimensional space with lots of noise.
And the ground truth is simple. One connected component and one hole or cycle.
Exactly. They used a tool called persistent homology to measure the holes in the data structure to see if the models could find that circle again.
So what happened when the standard Euclidean transformer tried to learn this perfect circle?
It failed.
Yeah.
Completely. Because of that geometric capacity bottleneck, it couldn't encode the topology. It failed to close the circle. It just produced this messy, dispersed line.
Its structural misalignment score, the GW cost, was high?
Very high, around 0.350. It broke the circle.
Yeah, the LMT.
The LMT, with its Lorentz geometry and the HA core and dynamics, successfully recovered the topology. It found the correct structure, the correct number of holes, and had a dramatically lower GW cost of 0.042.
So that's the proof. The geometry and dynamics combination can capture this global structure that flat models just miss.
It's a foundational proof that the right geometry matters more than just parameter count if you care about preserving structure.
Okay, so the second experiment tested the safety profile, the phase transition experiment. They intentionally put the model under stress by adding a global damping factor.
This was their way of simulating what happens when real-world data starts to shift or the system is under pressure.
Yeah.
They wanted to watch the mechanism of failure.
And they had a prediction.
A very specific, falsifiable prediction. The Euclidean model would show that smooth, linear, zombie-like degradation. The LMT was predicted to show a sharp collapse, a discontinuity, at a critical point.
And what did the results show?
They found a sharp transition point. Below a certain threshold, the model was stable, it held the structure. But once the damping went past that point, the structure couldn't hold and it just collapsed. The model failed cleanly and visibly.
Just as they predicted.
And the Euclidean model, it just got smoothly worse and worse across the whole range. The zombie model, exactly as predicted.
It's the difference between a system that says, I'm structurally compromised, halt operations, and one that just keeps lying with increasing incompetence.
And being able to measure that geometric frustration means you can monitor for that structural stress in real time and trigger a clean shutdown.
Okay, so we've laid out the theoretical case. The LMT is mathematically superior for handling hierarchies, for preserving topology, and for offering a safer, more interpretable failure mode. But now, we have to face the hard technical reality.
And we have to be aggressive about this reality. The LMT, as designed, is extremely slow. Again, intentionally so.
Right.
Section 8 in the paper lays it all out. It involves these expensive remaining operations, these exponential and logarithmic maps you need for the manifold, and it uses full quadratic attention. The complexity is ON2T.
I was looking at their comparison table, and the numbers are they're sobering. LMT throughput is estimated around 400 tokens per second.
Which sounds fast until you compare it.
You compare that to an optimized model with flash attention, which is doing something like 12,600 tokens per second, or even Mamba at 8,500. It's not even in the same ballpark.
It's orders of magnitude slower. And that fundamentally positions the LMT as a research instrument. It is not a deployment candidate today.
It's sacrificing speed for that foundational insight.
The cost of guaranteeing structural integrity with this level of explicit geometric enforcement is just too high for commercial use right now.
But accepting that this structure is necessary, it shifts the entire design philosophy for how we build AI in the future. What does the paper suggest that future looks like?
It proposes this really profound shift they call substrate engineering. For years, AI has been all about scaling. Brute force, Bigger chips, more parameters, bigger data sets.
And substrate engineering says that approach is hitting diminishing returns, at least structurally.
Exactly. Instead of just building bigger models, we should be choosing the correct geometric material for the informational task at hand.
It's like a civil engineer choosing between steel or concrete or carbon fiber based on load requirements.
That's the perfect analogy. We move architecture design from just encoding these weak biases, like in CNNs, to selecting curvature and dynamics as first-class design variables. The main question changes from how big can we make it to what is the specific geometric foundation that guarantees coherence.
This sounds like it's in direct competition with models like Mamba or Hipformer, which are all about efficiency.
The authors argue it's complementarity, not competition. They're solving different orthogonal problems. Hipformer is about making hyperbolic attention efficient, getting it to ON. Mamba is about solving long-range dependency efficiently.
They're focused on speed and memory.
While LNT is focused on the geometric solution to the binding and structural alignment problem, using that expensive ON2 math.
So the realistic future isn't a pure LMT, but maybe some kind of hybrid architecture that combines these strengths.
That's the vision. Imagine you start with an efficient backbone, maybe something like Hipformer's linearized attention, which is ON.
And then you add in sparse H-acorn layers.
Exactly, sparse. You wouldn't run the expensive ON2 dynamics on every token and every layer. That'd be crazy.
You'd apply it selectively.
Maybe at a few critical depths in the network to act as these structural checkpoints. Or maybe you'd only run the synchronization on the top K most important tokens, where K is way smaller than N.
And that brings the computational cost way down. You get the efficiency of the ON backbone, but you still get the geometric guarantees where they matter most.
It reduces the complexity from a crippling ON2T down to a much more manageable ON plus OK2T. That's substrate engineering in action, using the costly but guaranteed material only where you need absolute structural enforcement.
And crucially, that hybrid approach lets you do runtime monitoring. You could run the full, rigorous process just to generate that geometric frustration metric.
That's the ultimate safety mechanism. The LMT isn't just an engine, it's a structural integrity monitor. If that frustration metric spikes, the system doesn't wait for the output to become garbage.
It initiates that clean, abrupt collapse.
It reports, I am structurally compromised, and it stops providing potentially dangerous answers.
So this paper really establishes the theoretical sufficiency of these geometric dynamical architectures for preserving topology and, by extension, coherence. That is a massive contribution that pushes us beyond just brute force scaling.
It really is. The ultimate challenge isn't just more compute. As the paper concludes, the key is understanding when geometry constrains learning and when it liberates it.
It makes a powerful case that the quality of the representational foundation is just fundamentally more crucial than sheer computational strength. We need models that are structurally sound and honest about their own limits.
A great reminder that sometimes slowing down and prioritizing the mathematical foundation over speed is what gives us the insights we need to build truly robust and trustworthy systems.
The journey to structurally honest AI is clearly just beginning.
And papers like LMT are drawing the necessary roadmap, using geodesics and negative curvature.
If this deep dive into geometric foundations has sparked your curiosity about the math behind AI safety, we really encourage you to look further into some of the concepts we touched on.
Yeah, exploring persistent homology, that tool they use to measure the Betty numbers, or reading up on the original Kuramoto model for synchronization.
It'll give you an even deeper appreciation for this complex interplay between structure and dynamics that this paper gets at.
Understanding the shape of knowledge really is the first step toward building intelligent systems that we can actually trust.
Until next time, keep diving deep.